So I hope
Ma'am,
you see the PPT now, better. You can see the PPT.
Yes, ma'am.
Yes, ma'am. Yes, ma'am. Yes,
Okay.
ma'am.
So execution unit is a part of your CPU. Okay. CPU already a little bit you understand the architecture. What are the components you can see in this? Normally we have the two components ALU and CU, but to execute the instructions and also the to control the whole computer systems, we have many other components, that is a general purpose registers, dedicated registers, and some hardware or firmware where we can store some small code with the help of ROM, RAM, and flash memory. And we have obviously ALU and CU. So all these components already you have seen when I have explained the 8085 architecture. So registers means normally we have the two type of registers here: general purpose register and dedicated register. General purpose registers means accumulator is one of the example, and dedicated register you can say that program counter is there, and stack pointer is there. So they always store the memory address. So some registers we can use for storing the address and data, that basically the general purpose registers. But in your dedicated register you cannot store the data, always it will store the address. Okay. Now few registers here I have given, but you have more than that to control the internal components of the CPU, and as well as the to control the other than the CPU, whatever the components are in your system. Now PC program counter, that is also called the instruction pointer, stack pointer, instruction register. Instruction register is a very special register that can store only the instruction code, that means of code. Memory address register, memory buffer register you can see, and also the PSW, that is nothing but it is the accumulator and whatever the flags you have. So the combine this together you can have the program status one. Okay. So it is a 16-bit you can say, based on if you think the 885 architecture, but if you have the any other architecture that means 806, it is the different, depends on that how many flags bits you have, or how many flags you have in that processor, and it combined with some accumulator, or like accumulator there is any. Hello, please mute better your. Okay, so these are the common registers, but maybe you have more than that to control the internal components of your CPU, as well as if you interconnect with some devices, on that moment you have many registers. Now, whatever it is, now we can do some operations on that registers, then you can say that general purpose register. So here for general purpose register you can store, you can retrieve, and you can do some operations, for example shift operations. So in our execution unit, whatever the operation, execution unit means that it can execute different type of arithmetic and logical operation, isn't it? So during that time, during execution of the different type of arithmetic and logical operation, we need some different type of the shifting operation. So what are these we can observe? That is a right shift, left shift we can have, and we have the logical right shift, logical left shift, or we can have the arithmetic right shift, arithmetic left shift, and we have the different type of the rotating. That means that left rotating, that may be the right rotating. Okay. Now what are the differences, all this? Now you can understand the logical right shift, that through this table I have drawn the figure, and see that here right shift means that that is a LSB of your LSB of your number, it will be lost, and MSB will be vacant on that moment, and that will be filled with zero or zero. Okay. So this is the logical right shift. So right shift on that moment, obviously left shift where it will go. So it may be lost. Okay. Sometimes it may be controlled by with the help of any other flag registers. Sometimes we can do in our different processor can handle the different way, and that depends on the you can see that based on your operation, what are you doing? You are doing the addition, you are doing the multiplication, you are doing the division. So based on your requirement, you can do the different type of the operation, and if obviously if it will support by the architecture. But normally logical right shift means that LSB will be lost, and on that moment obviously MSB will be vacant, and that will be filled with a 0. And left shift, logical left shift means that, so on that moment MSB will be out, and LSB you can append with the help of logic value 0. But for the arithmetic operation, what is happen? MSB, if it is 0, on that moment that vacant bit will be filled with your MSB. That will be 0. And it is 1, then it will be 1. So normally what is happen in our computer system, logic value 0, 0 represent the positive number, 1 represent the negative number. So arithmetic right shift on that moment, whatever is happened for the logical right shift, that is LSB is lost. On that moment here is also LSB that may be lost, and MSB on that moment due to the right shift, MSB will be vacant on that moment. That you have to fill with the same MSB value. If it is 0, then it will be 0. It is 1, then it will be 1. Okay, so in that way you can do the right shift. But for the left shift, arithmetic left shift and logical left shift, there is no difference. Now rotating operation, obviously D0 bit, that means you can say that LSB will go to the MSB, and for the left shift, MSB will go to the LSB. Okay, so this is the rotating operator. It is a very easy. So everything we can do with the with the different type of operation, with the different type of the hardware support, and that depends on the type of the operation. What type of operation means? Operation means that suppose if you are doing the multiplication or you're doing the division, depends on your requirement, you can do the different type of the operation. Here suppose arithmetic right shift, you can observe when I will explain the boost multiplier circuit. That circuit uses that type of, this arithmetic right shift is used. Okay, so depends on the operation, you can use the different type of the shifting operation. So this is the just example I have given. Arithmetic shift operations, see that 0, 1, 1, 0, 0, 1, 0, 1, this number. So after right shift, 0 will be MSB again. Okay, and for the 1, it is 1. Now, how to design that design also different that you can design in your you can say that in your requirement, or whatever you you want, or whatever you desire. Based on that, you can draw the block diagram and you can design, and that should fulfill at least few operations. Few operation means basic operations are, we know that we can store, we can retrieve, and at the same time we can do the some shifting operation. So these are the main basic operations of your general purpose registers. So here you can observe that for 4 external inputs it is taken, and 1 output is their Q. And this cell is designed with the help of 4:1 marks. 4:1 marks means that line 0, line 1, line 2, line 3 can be connected to the output of the marks, and 4:1 marks. So obviously 2 select lines you have to consider. So S1 and S0. So 4:1 marks means that 2 to the power 2, that is the 4. So depends on the select lines, you can select the input lines. Okay, select lines and input lines are the different for your marks. If you forget the multiplexer, the architect multiplexer design, please you study from your previous book, that is Maurice Meno. So now here 4:1 marks means means that when S1 and S0 equals to 0, 0, line 1 will be connected to the output line of marks, and whatever the content of the line 0, that means whatever the value line 1 carries, that value will be transmitted to the output line. It acts just like a switch. Okay, now S1 S0 is 0 1. On that moment, line 1 will be connected to the output line of the marks, and whatever the content of line 1, that will be transmitted to the output line of the marks. Same as for line 2 and line 3. So S1 and S0, this is the two select lines. Maximum combination is 4. So 4 input lines we can select. Now whatever the contents of the input lines, that will be transmitted to the output line. So with the help of 4:1 marks, we can take the 4 external inputs, and all these inputs we can store with the help of single D flip-flop. So at a time, 1 bit data we can store. That may be from the line 0, that may be from line 1, that may be from line 2, or that may be from line 3. So at a time, 1 bit value from external environment we can store into the D flip-flop. Okay, this D flip-flop is one bit. Okay, single bit D flip-flop you can have. So you know the clear function. Clear is whenever you want to clear the circuit, that means you want to get the output value 0. So on that moment you can give the clear, that will be 0. On that moment Q will be 0. So this is the basic architecture of your general purpose register, single bit general purpose register. This register capable to store the 4 different type of the external inputs. Now, with the help of that basic structure, what are the operations you can do? Here you can see for the line 0 of the all cell, 4 basic cells we have considered. So all the 4 basic cells, what we have, the 4 input lines, line 0, line 1, line 2, line 3. For the first, second, third and fourth, all the cells have 4 input lines, that is line 0, line 1, line 2, line 3, and 4 another control lines you can say, that is S1, S0. These two are the select lines, and clock, that is the clock input line, and CLR, that is a clear to clear the this register. Okay, so what has happened? First input line 0 for all the cell you can observe that are connected with the whatever the outputs Q0, Q1, Q2 and Q3. So obviously you can say that if S1 S0 equals to 0, 0, so whatever the previous value, that will be continued. So no operation is done here, just whatever the outputs previous outputs, that value you can have the next block bus. Okay, so first line, that first input lines, that is a line 0. Through the line 0 you can give the inputs, that is Q3, Q2, Q1, Q0. That means outputs of the all registers, that is Q3, Q2, Q1, Q0. You can give the input to all the basic cells. See that for the first Q3 is input, and for the second Q2 is the input, input your what is the line 0. Okay, and Q1 is also Q line 0 input, and Q0 also the line 0 input. So in this way you can say that for the S1 S0 is 0, 0. On that moment, whatever the previous value, that will be input. And now check that S1 S0 equals to 0, 1. So what will be happen? 0, 1 means that line 1 will be connected to the output of your marks, and it will be going to your D flip flop. Okay, and ultimately next clock bus you will get the output. Now what is happened? This line is connected your you can say the right shape. See that Q0 is connected to the line on of the second cell, and Q1 is connected to the and to see that Q0 is connected to the, no, sorry, this is the right shift. So Q3 should be connected to the Q2 Q2 cell, and Q2 will be connected to the Q1 output cell, and Q1 will be connected to the Q0 output cell. Isn't it? This is the right shift. See that Q3 is connected to the Q3 is connect to the line 1 of the second cell, Q2 is connect to the line 1 of the third cell, and Q1 is connect to the input of the last cell. That's it means that LSB, you can say that. Okay, last cell you can give the input. So line ones are connected in such a way that you can shift to the right. Whatever the bits you have, that you can shift to the right. And now check that line 2 of all the cells. Line 2 of the cells, you can see that Q0 is connected to the second cell, Q1 is connected to the third cell, Q2 is connected to the third cell, okay, fourth cell. Okay, so in that way it is connected. So for the S1 and S0 equals to 1 0, that means line 2 will be connected to Q lines. On that moment, Q0 will shifted to the Q1, and Q1 will be shifted to the Q2, and Q2 will be shifted to the Q3. Okay, in this way it will be connected. Now for the 1 1, it is a very special, it is not the shifting operation. It will on that moment circuit will load the external value with the help of Q3, Q2, Q1 and Q0. Now check that all the input lines Q3, Q2, Q1 and Q0 directly connect to the line 3 of all the cells. So when it is possible, when S1 and S0 will be 1 1, on that moment it is possible to load the external value, okay, with the help of this basic cells. So these are 4 operations you can do with the help of this structure. So 0 0, no operation means that previous value will be continued. 0 1 means that is a shift right operation, 1 0 for shift left operation, 1 1 for parallel load operation. So whenever you design the circuit, on that moment you just first assume that what are the operations you want to do. Based on that you try to connect the all the lines. If you want to the right shift, so for which selection line you want to use for right shift, so on that on that moment you connect in this fashion. So here 0 1 is using for your right shift, so for that reason line 1 is used, or line 1 of all the cells are used for the right shift, and 1 0 is used for the left shift. So 1 0 means that 2, so I2 lines are connected in such a way that you can shift to the left. Okay, so based on your requirement, based on your truth table, easily you can design your circuit. Now this circuit, that what you have designed last, that is with the flip-flop, it will take the time. Okay, it depends on the clock, but we can design the same. Yeah, better.
Ma'am, I had a question. Ma'am, in the previous slide, ma'am, I didn't understand one part of the truth table. Ma'am.
Yeah.
Ma'am, in the CLK, ma'am, what is like in the remaining inputs, like ma'am, what is written over there? I didn't get it. Is it rising edge?
Clock is here depends on your D flip flop. Okay, beta. You can know that different type of the flip flop we have. That is a positive edge trigger, negative edge trigger, isn't it? So here is considered the positive edge trigger. So inputs, whatever the inputs are coming from the previous outputs, check that all the inputs are coming from the previous outputs except for the last case, that is 1 1. For 1 1, that for that case the loading operation is done with the help of the external input. But for other cases, what you are doing, all are considering the previous output line. So depends on the clocks, it will go to the outputs of the next output you can have the in the next clock pass. So Projita, what is your question, beta?
Ma'am, actually, I didn't know that it was positively edge triggered, ma'am. That's why I was confused, ma'am, from the signs. That's
Okay,
what happened.
good. Okay, good. Nothing. This depends on you, how what you have designed, and maybe you can design with the help of the level trigger. So normally we know that level trigger means that latch. In our execution unit, many times we use the latch circuit instead of your that is a level trigger. Okay, so that depends on you, what type of the execution unit you want to design and what is your requirement. Depends on requirement, you can use a different type of the structure of flip-flop or latch. Okay. Now, this circuit also we can design with the help of the combinational circuit. So last circuit you have designed with the help of sequential circuit, but also we can design with the help of combinational circuit. But what is the advantage? Advantage is that it is a faster circuit you can have. Because of that, the sequential circuit always depends on your clock frequency. Now, what are the operations you can do? Here is you can do the operations, that is for 0 0 you want to no shift, that means nothing, whatever the inputs that will be the outputs. And if you want 0 1, only one left shift if you want to do, 1 0 if you suppose twice, and for 1 1 you want to do the thrice. So in this way, in this fashion, you want to shift, and you want to design a combinational shifter circuit. Okay, and this is called the 4 by 4. And you have seen in your digital electronics class how to design the multiplexer. Okay, so same way we can write the expression y3 y2 y1 y0. So from the truth table also you can understand y3 is s1 s1 bar s0 bar, on that moment input will be i3. Okay, S1 bar is 0 bar, on that moment I2. S1 is 0 bar, on that moment I1. In that way, you can write whole the Boolean expression. I hope this is you don't have any problem for the for finding the output lines y3, y2, y1, and y0. From the truth table, we can write these expressions. Now, these expressions, whatever y3, y2, y1, y0, that is basically the multiplexer. Okay, so we have the external inputs, that is I0, I1, I2, and I3 for your S1, S2 equals to S1, S0 equals to 0, 0. On that moment, I0, uh, I3 is connected to the first input of your multiplexer. I2 is connected to the second input of the multiplexer. I1 is connected to the line 0 of the third, and I0 is connected to the input of line 0 of your last multiplexer. Okay, so in that way, first input of your multiplexer, that is line 0 multiplexer, line 0 line of your all multiplexer, you connect the I3, I2, I1, and I0. I hope you understand. This is the first step. And now second step is, because for the first step, S1 and S0 equals to 0, 0. On that moment, you want to get the value y3, y2, y1, y0 equals to I3, I2, I1, I0. That means you don't want to do any shifting operation. For that reason, you have whatever the inputs, that will be the outputs, and that is controlled by the output enable bar. This is a tri-state buffer circuit, so it is depends on the enable line, it will give the output values. Now for the S1, S0 equals to 0, 1. So obviously line 1, how you will be connected? You want to do only the left shift. Only once you want to the left shift. So for that reason, what has happened for the first marks, line 1 is connected to the I2. Okay, and second is I1, third is I0, and last one will be I minus 1. So you can see in your truth table. So depends on your truth table, you just connect all the input lines. Same as line 2 of all your marks. Line 2, what is done? So you want to do the S1, S0 equals to 1, 0 for this case. So 1, 0 case, what is happen? Y3 will be I1. So I1 should be connected to the I2 for the first marks. I0 will be connected to the, sorry, 1, 0. Huh. I1, I0, I minus 1, and I minus 2. So this is your two, from the truth table I can observe. So that way we can connect to the line 2 of all the marks. So first one is I1, next one is that I0, and next is that I minus 1, then I minus 2. Okay. Now for the last, you can see that 1, 1, either line 3 for all the marks. What is happened? I0, I minus 1, I minus 2, I minus 3. You can observe from the truth table. These are the inputs for the Y3, Y2, Y1, Y0 outputs. Okay. So for that reason, for the first marks, I3 is connected to the I minus 1.
Ma'am, you're not audible, ma'am. I'm on mute.
Hello, ma'am, you are not audible.
Ma'am, you're not audible, ma'am. Ma'am, ma'am, you're on mute.
Sorry. Am I audible now?
Yes, ma'am, you're audible now, ma'am.
Yes, ma'am.
Sorry, wait. Last this PPT you understood?
No, ma'am, yes, ma'am, we were at internal schematic, ma'am. We started that off.
No, I can explain from here.
Yes. Ma'am,
Okay.
from inter yes, ma'am. Yes, ma'am.
Okay, so this is the 4x4 shifter, and this 4x4 shifter, what are the operations it can do? These are the four operations for the values of S1, S0, 0001, 1011. For 00, what has happened? Whatever the inputs, that will be the outputs. That means Y3, Y2, Y1, Y0 equals to I3, I2, I1, I0. And for 01, what will be the output? Y3, Y2, Y1, Y0 will be I2, I1, I0, I minus 1. Okay. And for 10, S1 is equals to 10, output Y3, Y2, Y1, Y0 will be I1, I0, I minus 1, I minus 2. And for the last case, 11, S1 is 0. That will be the case. Then what will be happen? Y3, Y2, Y1, Y0 will be I0, I minus 1, I minus 2, I minus 3. So three times we want to shift to the left. So for that reason, we need the extra 3 bits. So all total, we have the 7 inputs from the external. Okay, from the external environment we have the 7 inputs. 4 original we have, I3, I2, I1, I0, and another 3 we require for your shifting, 3 times shifting. Okay, so 7 inputs and 4 outputs, and 2 control lines are there, select lines and output control bar. That is a with the help of the that is a buffer circuit, tri-state buffer circuit. We can sometimes want to read or we don't want to read. Okay, so depends on that, we can have the value y3, y2, y1, y0. Now this connection, how it will do, you can do with the help of the truth table. So all the marks, if you consider the first line, line 0, on that moment S1, S0 equals to 0, 0. So what are the inputs? I3, I2, I1, I0. So obviously for the line 0, for all the marks, you connect directly from I3, I2, I1, I0. So for the first marks I3, second marks I2, third marks I1, and last marks will be I0 will be connected. So on that moment, output Y3, Y2, Y1, Y0 will be I3, I2, I1, I0. Now for the S1, S0 equals to 0, 1, on that moment line 1 will be connected to the output of the marks. So all the line 1 you connect depends on your 0, 1. So what is the 0, 1? 0, 1 means that I2, I2, I1, I0, I minus 1. So first you connect the I2, second you connect the I1, third you connect the I0, last you will connect the I minus 1. Same as for 1, 1, what are the outputs? I0, I minus 1, I minus 2, I minus 3. So line 3 will be connected according to your inputs. So line 3, for line 3, you should connect for the first marks, that is I0, second marks you connect the I minus 1, third marks you connect the I minus 2, fourth marks you connect to the I minus 3. So in this fashion you can connect and you can have the 3 times shifting operation. Now this circuit is okay, better. It's very easy. First understand the truth table. What are the outputs you need? Based on that, you just connect all the lines. Now, with the help of this circuit, you can design 16 by 4 shifter. How you can design? Now, again, you have to find out the outputs. If you can draw the truth table, easily you can connect all the lines. So, what is your requirement? That is for 0, 0. Whatever the inputs, that will be the output. So, y equals to x. And for 0, 1, you want to shift to the left, and this is a rotating, you want to rotate. That's why x0 position will be filled with x15. Okay, so it is a left shift. 0, 1 is one time you want to do the left shift. So y1 equals to x0, then y0 position will be vacant, and that will be filled with the x15 because you want to rotate. Now, so for the 1, 0, what will be happen? You want to do the 2 times rotate to the left. So on that moment, y1 and y0 will be filled with x15 and x14. In this way, 1, 1 case, when you again you want to shift to the left, so y3 will be x0. On that moment, y2, y1, y1, y0 will be filled with your x15, x14, and x13. So this is the truth table. Now, based on this truth table, easily you can connect the lines. Now, see that whatever the values of your last means that from the right, you can consider the last marks. There is a I minus 1, I minus 2, I minus 3 are connected to x15, x14, and x13. You can connect x14, 15, 14, 13 to the I minus 1, I minus 2, I minus 3 of the last marks. Okay, and others are doing in the same fashion what you have done the last circuit. Okay, same way you can do. So you want to rotate to the left. Okay, if you want to rotate to the right, on that moment x0, x1, x2 will be connected to your from the right, if you consider the marks, for the first marks I1, I minus 1, I minus 2, I minus 3 will be connected to x0, x minus x2. So depends on your right shift or left shift, you can connect all the lines. So I hope you can design this circuit also. Now 16 by 16, it is a barrel shift register. It is a very big circuit. You will try first. If you can't, then I will explain. Okay, from the Rafiquzzaman you will try. Already explained this circuit. Now uh, one of the important circuit, that is the adder. You know that with the help of adder circuit, anything we can do. We can do the addition, subtraction, division, multiplication, everything we can do with the help of adder circuit. So that you have designed in your digital laboratory class, or sorry, digital reference class, that is a 4-bit ripple carry adder, and you know the truth table, and also you know the expression. If you know the expression, usually you can design the circuit. So this circuit is known to you. Now, this circuit also SR ma'am has explained in your last semester class. That is a carry look ahead adder circuit. Carry look ahead adder circuit. I just give few things I want to explain, and based on that you will design the 16-bit, 32-bit, and 64-bit design. What is happened for your carry look ahead adder circuit is that same expression you can write in this way, that is xi yi plus xi yi and ci. So that you can write xi yi as a gi, and xi plus yi you can say that pi. So ci plus 1, that you can write gi plus pi ci, where g is called the carry generate function and p is called the carry propagate function. So from the expression, usually you can understand that when xi and yi, or you can say that x and y both are the 1 obviously it will generate one carry. So it is called the carry generate function. At the same time, x and y, if anyone is 1, if any propagated carry is there, on that moment it can generate the carry ci plus 1 equals to 1. So one is the carry generate function, another is the carry propagate function. Now see the expression, that is ci plus 1 equals to gi plus pi ci. Now if you consider I equals to 0, on that moment you can write c1 equals to g0 plus p0 c0. In that way, if I equals to 3, you can write c4 equals to g3 plus p3 c3. So now for the first, c1 equals to g0 plus p0 c0, that c0 represent the first input, carry input, c in basically. Okay, now in your C2, C3 and C4, if you replace C1 with C1, C2 and C3, ultimately you have an expression for C2, C3 and C4. For each case, you can see that all are depends on the initial input, that initial carry input, that is C0. Whatever the intermediate carry, that is not required basically. So directly you can compute the C4, you can directly compute the C3 and C2 also. So obviously from these carry inputs, if you can compute, so directly you can compute the summation value. So ripple carry adder, which takes the more time to compute your summation, but for your carry look at the circuit, it will take very less time to compute all the sum bits. So that's why it is a high speed, you can say the high speed adder circuit. But compare, if you compare the logic gates, that means overhead, if you compute, on that moment it will take a huge space. Okay, it needs many gates and many space it will take compared to your ripple carry adder. Now with this all the carry generate and carry propagate function, you can find you can get from your simple basic adder circuit. Okay, g0 means that what has happened, g0 means that x0 y0, g1 means that x1 y1. In that way, with the help of the basic adder circuit, if you have the inputs x and y, easily you can compute the g and p, because g and p are depends on the x and y, nothing else. Okay, it doesn't depends on the carry. So all g's and p's in a single step you can compute. Now carry look at circuit, that circuit can generate all the carries, and at the same time g0 and small p0, these two are called the group group generation and group propagation function. Okay, propagate carry, you can say that. Okay, so these g and g0 and p0 you can use when you want to design a higher level of carry look ahead adder circuit. Now this circuit is helpful to design to your complete carry look ahead adder circuit. This circuit, the previous circuit is only only to find out all the carries. Okay, but here with the help of this you can design all the sum bit. Now for the 4 bit, if you consider, so if you can give all the inputs of the x and y, x0, x1, x2 and x3, and y0, y1, y2 and y3, with the help of the basic adder you can have all the g0s and gis and gpis, that means g0, p0, g1, p1, g2, p2, g3, p3, and all the inputs of your carry looker circuit, that can generate all the carry, and that carry you can give the inputs of again basic adder. Okay, so that basic adder circuits are the inputs x, y, and also the carry, and obviously it can generate all the sum s0, s1, s2 and s3, and carry look ahead circuit which can generate all the carries. From that you can have the last carry c4 and g0 and p0. So I will request you, please you find out the total computation time, total add time for this circuit, and if you consider the 4-bit ripple carry adder, then you can understand that how fast it is. Okay, and maybe if you consider the 16-bit or 32-bit, you can understand that what is the difference between these two type of circuit. Two type of circuit means that one is that carry look adder circuit, another is that is a ripple carry adder circuit. So if you compare these two circuit, you can understand that how fast it can compute the addition. Okay, now this circuit is known to you because last semester you have done. Now this is also you have done, this is called the serial adder circuit. So last, what is happen, the carry looker adder circuit or ripple carry adder circuit, we can say that 4-bit adder circuit, 16-bit adder circuit. So depends on the inputs you have, the depends on the bits you have in your number. Based on that you should have that bit number of inputs of your circuit. Okay, if you need the 16 bit, on that moment you should consider the x and y is the 16 bit. Okay, on that moment 16 basic sales, basic adder circuits you should have. On that moment 16 bit you should consider in your 16 CSC circuit. Okay, so all inputs depends on your what is the number of bit you have considered for your adder. But here for the serial adder x and y, any number of bits you can consider, arbitrary length of the inputs you can consider for your serial adder. I just want to ask you, can you remember this circuit better? Serial adder circuit. Can you remember this circuit, Prajota?
Yes, ma'am. Yes, ma'am.
This is a very interesting circuit. X and Y, you can consider the arbitrary length. That means depends on the clock. You can give some length. That means it can work with 4, it can work with 8-bit, it can work with 16-bit. But only two numbers it can add. Okay, two numbers. Each number can have the arbitrary size. X and Y depends on the time. It can consider the bits. Okay, first bit on the first clock, second bit it can consider the second clock. So x suppose 16 bit, y is 16 bit, so first bit will accept for at the time of the first clock, second bit will consider the second clock pulse, third bit will consider the third clock pulse. In that way 16 bit it will consider for the 16 clock pulse. Okay, so x and y you can consider any number of bits, but remember here only you can add the two numbers x and y, you cannot add the three numbers. Two numbers where each number you can consider the arbitrary length. Okay, so obviously if consider the two numbers and two lines, with the help of two lines we are doing, so two lines means that maximum value 1 plus 1, that will be the 2, and if you consider the previous carry, on that moment it will be 1 plus 1 plus 1, that means maximum sum it can generate, that is a 3. Clear? So 3, that is the decimal number. If you convert into binary number, that means that will be 1 1. So 1 1 1 1 you can use for the sum, another one you can use for your carry bit. So for that reason for the first circuit, that is Z. Z means that sum, that is a single bit, and carry out, it generates the single bit. Okay, so for the first circuit, what is happen? Maximum it can consider the 3 bit. So maximum it can consider 3 bit means that 1 plus 1 plus 1 it can be happen for the sum, that is a 3. If I consider the decimal number, and that decimal number, if you convert it in the binary, that means that will be 1 1. Only one value it will go to the Z, and another one it will go to the carry. So out of 2 you can utilize in this way. So only one single D flip-flop is sufficient to design this type of the circuit. Now obviously you can understand that this full adder circuit, if you draw the truth table, so what are the inputs in your truth table? That is X, Y carry in, and what is the output? That is a sum. So whatever your that basic circuit you have designed here for bit ripple carry adder, same truth table you can have, and same expression you have, and same circuit you have. So this full adder circuit you can replace with the simple your full adder circuit. Okay, this combinational circuit, full adder combinational circuit, is not different any of your basic full adder circuit, but just you include one D flip-flop. It is the difference. But now suppose if you want to design for the four numbers, you want to add 4 numbers, 4 arbitrary numbers, suppose 4 16-bit numbers, 4 16-bit numbers, suppose x1, x2, x3 and x4. Serially you are trying to give all the values. These are the serial input. You can consider the serial inputs. So 4 numbers if you want to consider. What will be happen in your truth table? Our first challenging task is that what should be your block diagram. It is little bit difficult, but you can understand how many input lines and how many output lines you have to consider, and how many D flip-flops you have to consider. Now see that D flip-flop, number of D flip-flop depends on the number of carry. Okay, check that number of carry, the number of carry that actually determines the number of D flip-flop. Now initially you consider the 4 numbers. So 4 number means that maximum value 4, 1 bit, what you can have 1 plus 1 plus 1 plus 1, and another input line, obviously 1 carry will be there, at least 1 will be there, so only single carry input line you consider. So initially if you consider the 5 input lines, x1, x2, x3, x4, and 1 is that carry. So 5 input lines initially if you consider, on that moment it will be 1 plus 1 plus 1 plus 1 plus 1, that means 5. So 5 you can represent in binary, that is a 1 0 1. So you can understand that at least 3 bits are required to represent your sum. Okay, so 1 bit always you have to consider the sum, and another 2 bit you can consider for your carry. So for that reason 2 D flip-flops are required for your block diagram. So obviously what will be the inputs? Your x1, x2, x3, x4, y1 and y2. These 6 lines will be required to the inputs of your combinational logic circuit. Okay, and obviously one output you consider for your summation value. Now if you draw the truth table, 6 inputs for the input lines, and output you can consider the Z, that means sum, another 2 bit for your carry, that means suppose C1, C0. So you can understand that in your truth table you have the 6 inputs and 3 output lines. Okay, so to find out the outputs Z, C1 and C0, you should have the 2 to the power 6 combination. 2 to the power 6 combination meaning is that 64 inputs you have. Okay, so with the help of CAD for VLSI you have one tool that is called the Espresso. Espresso is one of the software tool. With the help of this you can find out the optimized Boolean expression, and usually you can understand what should be the circuit. Now if you want to find out the Boolean expression from this truth table, the truth table which can have the 6 input lines and 3 output lines, so on that moment it will come around 53. 53 you can say that 53, you can say not the 53, 52 plus 1, 52 and expression, and 1 is the OR expression. So ultimately 53 and OR gate you need. Okay, so it is a huge amount of, a huge number of gates you need to design this type of the combinational circuit. This type of means that when you consider the four inputs, four number you want to add, on that moment you need huge number of the gates. So for that reason we never use the truth table, or never use this type of the gate to design the combinational logic part. Okay, so you know that any sequential circuit you have the two part, one is the combinational part, another is the sequential part. Sequential parts obviously we design with the help of the D flip flop or any type of the flip flop, and combinational circuit normally we use the and or not the basic gates we want to use. So for the first serial adder, that is a 2-bit serial adder, there you don't have any problem, only in a normal full adder you can replace. But for the 4 input you cannot design with the help of simple basic gates. Okay, on that moment you have to use the module structure. So whatever you design with the design for your 2-bit serial adder, same you can use for your 4, you can use for the 6, you can use for the 5, any number of inputs you can use the modular structure of the 2-bit serial adder. So whenever you will design the 2-bit or 4-bit stream or 5-bit 6-bit, you have to consider this is the diagram. This is the 2-bit. With the help of this 2-bit you have to design the 4, 5 and 6-bit. You will try first, then I will check that you can design or not. You have to verify, okay, that design is correct or not, then I will explain that if you can't design. Okay, so do you have any question, Beta?
No, ma'am. Will we get the slides for this today only, or will we get it after
Already,
this?
already I have uploaded, Beta, in your meet, no, sorry, team.
Okay, ma'am. Okay, ma'am. Thank
Okay,
you.
but you will try this circuit.
Yes,
Huh?
ma'am.
If you can't, then I will again explain. This already SR ma'am has explained for the 2-bit stem serial adder. With the help of 2-bit stem serial adder, how you can design the 4-bit, 5-bit and 6-bit. Okay, you will try first, and this another way you can design, that is directly with the help of the basic gates you can design the circuit, but it is very cumbersome. It is not, it is very tedious job. At the same time it will take the huge number of the gates, and it is very difficult to find out the simplified expression. So I will request you to design the 6-bit or 5-bit, whatever it is, a basic block diagram you should consider, that is a 2-bit stem serial adder. Clear? You have to practice, otherwise very difficult to design when you have exam. Clear? Okay, beta,
Okay.
I can stop here.
Yes, ma'am. Thank you, ma'am.
Okay, beta.